A comet from another star barreling in at 58 kilometers per second slipped into our solar system this July, lighting up telescopes and news feeds with wild speculation. But most of what you heard, alien engines, explosive outbursts, even chatter about a neon green flare, barely matches what scientists actually observed. A nucleus smaller than many predicted, an ancient age, exotic chemistry, and a signal roughly 5 times brighter than models expected. With its interstellar origin confirmed, yet its story far from finished, the real facts are stranger and more uncertain than the hype. So what has the data actually shown, and what questions remain as 3I/Atlas nears its closest approach? On July 1st, 2025, the Atlas survey in Rio Hurtado, Chile, recorded a faint, fast-moving speck against the star field. That single detection would soon upend the routine of minor planet monitoring teams worldwide. When the ATLAS group submitted their measurements to the Minor Planet Center, the orbital solution that returned was unmistakable. The object's path wasn't merely elongated, it was hyperbolic. Even after accounting for every gravitational influence in the solar system, the trajectory would not close. This wasn't a local drifter. It was an interstellar intruder on a one-time flyby through our neighborhood before it slipped away forever. The numbers tell the tale. 3I/Atlas is moving with a hyperbolic excess velocity, what astronomers call V infinity, of 58 kilometers per second relative to the Sun. That's nearly double the escape speed from the solar system at that distance. No comet or asteroid born here could reach that speed on its own. The only way to get such an open trajectory is to start from somewhere entirely different. Confirmation came fast. Within 24 hours, observatories around the globe raced to collect more data. Pre-discovery images surfaced from other Atlas units and from the Caltech Zwicky Transient Facility, pushing the earliest sighting back to June 14th. Each new data point tightened the orbital fit, and the hyperbolic solution only grew firmer. By July 2nd, the Minor Planet Center issued the formal designation 3I, the third interstellar object. But interstellar status is more than one label. Astronomers trace the orbit backward, far beyond the outer planets and into the dark between stars. The path aligns with no known solar system source, no planetary family, no ancient collision. This is a visitor from deep time. Based on its velocity and likely galactic trajectory, models place 3I/Atlas somewhere between 3 and 11 billion years old. That implies it may have formed before our own solar system finished assembling its planets. What sets this discovery apart from the headlines is the hard evidence. The orbital solution is public. Data from dozens of observatories are archived, and the math is straightforward. This isn't speculation. The hyperbolic orbit, the high V infinity, and the absence of any plausible solar system origin make the case airtight. This is the third confirmed interstellar object, and the first caught early enough for a full-scale scientific campaign, all of which means every hour is precious. 3I/Atlas is already racing inward, never to return. Telescopes capable of tracking faint, fast-moving targets are scrambling for time. The objective isn't just to watch a comet, it's to capture a messenger from another star before it fades into the dark. Long before the official announcement, 3I/Atlas had left a faint signature across the sky. Wide-field survey instruments built to catch transients and exoplanet shadows swept across its path. The Transiting Exoplanet Survey Satellite, TESS, was among them. In May and June 2025, TESS gathered full-frame images for its mission, but those deep exposures also covered the region where 3I/Atlas was silently drifting in from the outer darkness. When astronomers later mined the archive, they found a low, steady rise in brightness over several weeks. There was no sudden flare, no dramatic eruption. Instead, the object brightened at a rate consistent with a comet warming under increasing sunlight, just enough to draw the attention of people who track. Subtle changes. The magnitude sat around 20, then inched to 19.3 by late June. That number sounds faint, but for a cold, distant body near 4.5 astronomical units from the Sun, it signaled genuine activity. Not a dead rock, but a nucleus already shedding gas and dust long before it appeared in official discovery logs. That early activity matters. If a comet brightens far from the sun, its surface must be threaded with ices that sublimate at low temperatures, carbon dioxide, carbon monoxide, perhaps more exotic volatiles. Those materials make a comet unpredictable, volatile, and hard to model. For teams watching the survey feeds, the gradual rise was a wake-up call. This was not a fossil. It was waking up quickly. The test data and the pre-discovery records from ATLAS and ZTF set the stage for what followed. The object's light curve, the record of brightness over time, showed no obvious periodic flicker, no clear spin signal. If a rotation period existed, it was buried beneath the glare of the coma, masked by dust and gas streaming off the surface. Later, ground-based photometry would hint at a possible 16-hour rotation, but early survey data couldn't confirm that. What the surveys did deliver was context. 3I/Atlas was not a faint, inert speck. It was active, volatile, and already building a coma before anyone knew it existed. Those early light curves pushed astronomers to secure high-resolution imaging and spectroscopy, while the comet was still inbound and reachable. Every hour counted. A window like this, to study an interstellar visitor with advance warning, had never opened before. The race was on to turn that faint, steady brightening into real insight about what drives an interstellar comet. On July 21, 2025, the Hubble Space Telescope locked onto 3I/Atlas for a rare, high-stakes imaging run. The comet was streaking through the system at nearly 60 kilometers per second, and even Hubble's precision optics had to compensate. The resulting frames showed background stars smeared into streaks, a quiet record of how fast this visitor crossed the sky. But Hubble's real contribution lay at the center of the blur. In the heart of the expanding coma, astronomers obtained the first solid limits on the nucleus itself. Early brightness-based guesses had ranged wildly. Some suggested a nucleus as large as 10 kilometers, rivaling the biggest comets we know. Hubble's measurements pared that down. Careful photometry, subtracting the surrounding dust contribution, narrowed the diameter range to roughly 0.44 to 5.6 kilometers. The team favored a value well under a kilometer, small enough to fit inside Manhattan, yet substantial on a human scale. That range isn't trivia. Nucleus size governs much of a comet's behavior. A big nucleus can hold more ices, fuel stronger outbursts, and survive closer solar passes. A small one may fragment or disintegrate under solar heating. For 3I/Atlas, the new constraint ruled out many of the wild early ideas: giant spacecraft, planetary shards, or a disguised asteroid no longer matched the evidence. The object is simply too small to be anything but a cometary nucleus, laced with volatile ices and wrapped in dust. The Hubble team, led by David Jewett at UCLA, used a decades-honed technique: imaging through multiple filters and comparing the inner coma's brightness profile to dust-scattering models to pull out the faint nucleus signal. The method isn't perfect. At these distances, even Hubble can't fully resolve the nucleus from the haze, but the high angular resolution and careful modeling provided the best estimate yet of the comet's size. Those measurements didn't just tamp down speculation, they set up the next phase of study. Knowing the nucleus size lets astronomers estimate mass loss as the comet heats and compare that to familiar solar system comets. The dust loss rates inferred from Hubble appeared surprisingly ordinary. By that measure, 3I/Atlas looks less like an alien artifact and more like a natural object sculpted by billions of years of interstellar drift. But Hubble left a major question open. Composition. The images revealed a sunward plume of dust hinting at active jets or localized outgassing, but they offered no chemical IDs. For that, spectrographs are needed, instruments that split light into chemical fingerprints. The hunt for those signatures was already underway, with major observatories on Earth and in orbit vying for time. The James Webb Space Telescope, renowned for peeling back cosmic layers, turned its gaze on 3I/Atlas in early August 2025. On August 6th, JWST's NIRSPC captured the comet's infrared signature, splitting the coma's faint glow into a barcode of molecules. The results were unexpected. Most solar system comets wake when water ice sublimates and drives the classic jets and dust plumes. But 3I/Atlas wasn't following those rules. The spectral lines showed that, at this distance, carbon monoxide and carbon dioxide were doing most of the work. CO and CO2 dominated the gas output, while water vapor, normally the main actor at these distances, was a minor player. This chemical profile is uncommon. In local comets, CO and CO2 usually dominate only when the object is much farther out, too cold for water to react. Here, however, 3I/Atlas was already building a thick, active coma powered almost entirely by these more volatile ices. CO2 needs less heat to escape than water ice, so it sublimates at lower temperatures and can drive activity far from the sun. JWST showed that this early activity wasn't a gentle simmer. The gas output was strong enough to drag dust grains into space and build the coma visible from Earth. But there was a twist. The dust wasn't behaving as expected. Instead of forming a classic tail streaming away from the sun, much of it was being pushed sunward toward the light, as if radiation pressure rules had been reversed. That's not just a curiosity, it's a clue. A sunward dust plume likely means grains are launched by sudden gas bursts, perhaps from CO2-rich pockets near the surface. When those pockets rupture, they act like tiny geysers, blasting dust with enough force to overcome sunlight's push. The result is an oddly structured coma with a sunward spike that stands out against ordinary cometary haze. This behavior suggests a nucleus with a patchwork of volatile ices buried at varying depths, exposed by cracks or fractures. The pattern matches some of the most active comets we've seen, but the chemistry is inconsistent with a solar system origin. The CO, CO2, and weak water signature point to formation in a much colder environment than our own comets experienced. In short, 3I/Atlas carries a chemical memory of another star's protoplanetary disk, frozen for billions of years, and now thawing for the first and only time as it races past our sun. JWST's spectroscopic team, led by comet chemistry specialists, continues untangling the full molecular inventory of the coma. Even the early results are rewriting expectations. The dominance of CO and CO2, the sunward dust spike, and the absence of strong water-driven jets all point to a comet shaped by alien conditions. It reminds us that not every interstellar visitor will match our templates. Some bring their own rules, chemistry, and stories, if we catch them quick enough. The next step is to watch how these gases interact with other coma species as the comet nears the sun. That's where ground-based spectroscopy shines, tracking the rise of CN and other fragments that signal breakdown of more complex molecules. For now, JWST's message is clear. 3I/Atlas is not just a visitor, it's a messenger carrying chemical fingerprints of a world we'll never see. Late August shifted the campaign. Gemini South, armed with the GMOS optical spectrograph, focused on the comet and captured a slender tail stretching roughly 0.1 degrees from the nucleus. For an interstellar object, even a faint tail is proof. The nucleus is shedding dust and gas under sunlight and the solar wind. That visible outflow marks the comet as active, not a frozen relic drifting by. Gemini's key finding came from the spectra. A distinct emission line from CN, cyanogen, stood out. CN, a carbon-nitrogen molecule, is a classic indicator of cometary activity, glowing as sunlight breaks apart more complex parent molecules in the coma. In most solar system comets, CN is accompanied by C2, diatomic carbon, and the C2 to CN ratio acts as a chemical fingerprint. Here, C2 was nearly absent. The C2/CN ratio measured below 0.09, placing 3I/Atlas in the class of carbon chain-depleted comets. This is more than a curiosity. In our system, comets with so little C2 are rare and typically come from the coldest, most distant regions. For an interstellar visitor, such depletion hints at formation far from its parent star or long exposure to cosmic rays during its voyage between the stars. Gemini's spectra from August 27th captured this moment as the comet's activity intensified near 3 astronomical units from the Sun. Gas and dust were unmistakable, but the chemistry was unlike most homegrown comets. As the tail extended and CN strengthened, astronomers got their first quantitative view of the physical processes shaping 3I/Atlas. Dust grains carried by escaping gas mapped the comet's path. The lack of C2 set it apart from nearly every other known comet. These findings didn't just add entries to a catalogue, they redrew boundaries in comet science and raised new questions about the dust itself, questions that soon took center stage. In summer 2025, polarimetry teams at the VLT in Chile, the Nordic Optical Telescope in Spain, and Rojan Observatory in Bulgaria trained on 3I/Atlas's coma. Their measurements revealed a light-scattering signature that defied known patterns. When sunlight scatters off comet dust, it becomes polarized, with degree and direction changing as the angle between Sun, comet, and Earth varies. Most comets show a modest dip into negative polarization at small phase angles, then a steady rise into positive values. 3I/Atlas broke that mold. Its minimum polarization, P to min, plunged to minus 2.77% at just 6.41 degrees, a value twice as deep as the most extreme comets in the solar system and confined to a much narrower range of angles. The inversion, where polarization flips from negative to positive, occurred at 17.05 degrees. The slope of the negative branch, how quickly polarization drops with angle, was a sharp 0.40% per degree. For context, even very dusty comets like Hale-Bopp or Boris dipped to only about -1 to -1.5% and over a broader phase angle range. Such a deep, narrow negative branch is more than an oddity. It's a fingerprint of the dust's microphysics. The numbers point to grains that are large, dark, and likely rich in ices or complex organics. The steep slope suggests highly porous, fluffy aggregates loosely bound, rare in the inner solar system. The low inversion angle, just over 17 degrees, resembles some rare asteroids and trans-Neptunian objects, but even those don't reach this depth. Modeling these curves requires advanced light scattering simulations, and only a narrow parameter set reproduces such extremes. The most plausible scenario: dust aggregates mixing ices and dark organics in fragile porous structures. Polarimetry maps showed little variation across the coma, hinting at a global process shaping the dust. No comet or asteroid has shown a polarization curve like this. Even 2I/Boris, the previous interstellar visitor, had a much shallower branch. The evidence points to grains formed under conditions colder and older than anything in our solar system, a new class of dust-scattering object born in the dark between the stars. On September 7th and 8th, as a total lunar eclipse drew many eyes skyward, a quieter pursuit played out in backyards and small observatories. Amateur astronomers with everything from modest DSLRs to more advanced rigs tracked a faint object drifting near the moon's shadow. 3I/Atlas, already stirring professional debate, became a focus for citizen observers. Their images, shared in real time across forums and social media, quickly sparked controversy. Several reported a distinct green hue in the coma, a color traditionally linked to diatomic carbon fluorescing under sunlight. But this time the story was complicated. Earlier, spectroscopic. Work by Gemini and the VLT found 3I/Atlas nearly barren of carbon chain molecules. The expected C2 signature, usually the culprit behind a comet's green glow, was missing or vanishingly faint. Yet online, raw and stacked amateur frames seemed to show unmistakable green. The question: real feature or camera trick? Some suspected the tech. Digital sensors, especially under the odd lighting of a lunar eclipse, can exaggerate colors or introduce artifacts. The moon's coppery light, atmospheric scattering, and the challenge of imaging a faint object against a bright, shifting sky all conspire to distort subtle hues. Without standardized calibration, reference stars, or controlled settings, these images are suggestive, not definitive. No professional observatory reported a green emission spike that night, and no peer-reviewed photometric analysis has confirmed the amateur claims. The episode highlights both the promise and limits of citizen science. Amateurs extend observational reach and catch fleeting moments, but without rigorous calibration, even striking images demand skepticism. The lunar eclipse, dramatic as it was, created a difficult environment for accurate color measurement.